Hey everybody, welcome back to another video. Alright, this section we're going to switch gears. Now that we've been talking about a whole bunch of trigonometric identities, how to prove identities and also how to simplify expressions using identities, the next couple sections of the chapter are going to involve solving equations. So remember, at the very beginning we talked about the difference between an identity versus an equation. And very quickly, the equation usually has few solutions. Only a couple values of the variable will make the equation true. Whereas an identity, it's true for all values of the variable. All right, so if you haven't read through the notes, I encourage you to just either pause the screen, read through them, because I'm not gonna spend time just reading through everything I've written here, just to kind of screen things a little bit quicker. But let's talk about this purple box here. It says how to solve basic trig equations. So what do we mean by a basic trig equation? So I'm going to write it in this format. It's kind of abstract, but let's think about what it's saying. T theta is one trig function, and c is some sort of constant. So what do we have in mind here? Let's maybe put a quick example. So it could be sine theta equals, let's say, I don't know, 1/2. So the t theta is going to be sine. That's one trig function. This constant c is 1/2. We can also do things like, let's say maybe we want to know, solve tangent theta equals to 50. Okay? Things like that. All right. Now, what's the advice I give here? So it says how to solve. So we have a couple steps. It says put a trigonometric equation into the form t theta equals c. What do I mean by that? Sorry. In other words, I'm basically saying put the trig function by itself on one side of the equation. And just for convenience, I'm going to always put that on the left side, but one side of the equation. Once you do that, my tip is to draw a unit circle, and you're either going to draw a line x equals to c or y equals to c to help you visualize the angles, remember the wet noodle, where they intersect. Once you've drawn that, you're going to determine the appropriate range of values for theta. That will give you the solution. So let's actually come back to these how to solve after we've done an example. So let's just start with example 1. And here's our problem. So we want to solve cosine theta equals -1/2. So it's already, step 1 is already done. It's already isolated in the right form. So the next bit says, okay, draw a unit circle. Okay, let's draw a quick unit circle here. Label our axes and just put a 1 here to remind us that this is radius 1. Okay. So next it says draw the line x equals c or y equal to c. Now, what do I mean by that? So again, our equation is cosine theta equals -1/2. So what I really am thinking about is I'm thinking, okay, remember of the definition of cosine of theta. Well, it's the x-coordinate according to the wet noodle or the radian theta. Okay, so remember it's the x-coordinate. So what I'm going to draw is the equation of the line x equals to 1/2, and I'm going to do it in red. So, and I'm sorry, x equals to -1/2. So -1/2 is, I don't know, somewhere right here. So I'm just going to draw the line x equals to -1/2. Now that I've drawn that, I'm going to go back and think, okay, what angles have x-coordinates so that I hit exactly these two coordinates for my terminal points? So I hope you can see that the answers are, okay, one angle is going to be, if I go from 0 along the top, that's going to be, theta is going to be what? So this is -1/2 for cosine. I believe that is, the reference angle is pi over 3 or 60 degrees. So if you think about it in terms of the whisker method that I like to draw, it's going to be the top whisker right there. Okay, so that's going to be 2 pi over 3. So immediately we can basically say, okay, theta is 2 pi over 3 is one of our solutions. But we can see that there's actually more solutions, right? There's another value that we intersect because the x value are vertically, right? So x values are here. All of those values on that red line have x equals to -1/2. And we're looking for where we hit the unit circle. Now there's one more angle. And I could either do it by going in the negative direction and doing negative 2 pi over 3. An equivalent way to do this angle, and let's do it maybe from the top and do it on the outside, it's this angle. So what would that be if we're going in the positive direction? So it's going to be using whiskers 1, 2, 3, 4. 4 pi over 3. Okay, so 2 pi over 3 and 4 pi over 3 are those basically where those red X markings are. Now, if we're going to solve this, we're going to say, okay, what are the solutions? So now let's go to the third kind of bullet point here, and let's talk about this. Okay, so determine if there are any restrictions on the range of theta. So if there's infinitely many solutions, that means that there's no restrictions. So 2 pi over 3 and 4 pi over 3 are just 2 out of infinitely many radians where we can circle around this for forever, over and over and over again, and we'll always land back at the same spot. So if I'm only interested in just one of these, then I just put 2 pi over 3. But if I want all of them, I'm going to do plus 2 pi k, and remember k belongs to an integer, so I'm going to put z with a little extra stick. Alright, so that takes care of infinitely many solutions where I'm going to hit basically in that corner. If I do 2 pi, I'm going to go one full turn, one full turn, one full turn. Or I can even do turns in the backwards direction, but I'll always land at just the 2 pi over 3, basically. Alright. Now, if I want to include all of my solutions for this part, well, then I'm going to say, okay, theta can equal 4 pi over 3 plus 2 pi k. K belongs to z. If you instead chose to write negative 2 pi over 3, perfectly acceptable answer as well. But at this point, I would say box your answer. This is how we write it. Because again, it says to find all solutions, and there was a little bit of a hint here that I wanted all of them. So infinitely many, but there's kind of two different branches. There's the 2 pi over 3 version and the 4 pi over 3. Okay, so those are all of my exact answers. We'll talk a little bit more about restrictions a little later, but this is a great place to start. Okay, now that was the unit circle approach. I've loved this method. This is my preferred method of solving it, but I want to give you another approach as well. Okay, so, and I'm going to do it by just going to Desmos. So before I open Desmos, let's switch our gears and do this. Y equals cosine of x, so I'm going to graph cosine. And then I'm going to graph y equals -1/2. And essentially, I can rephrase this equation in green right here. I can rephrase it by basically saying, okay, if I want to solve cosine of theta equals -1/2, it is the same to ask where do these two graphs intersect. So to do that, I have to know how to graph cosine of x and y equals to 1/2. Now, actually, before I open up Desmos, let's actually do it by hand. See how good we can draw this. It's not going to be too great, but... So let's start with cosine. Remember, cosine bounces between 1 and -1, and it has period, let's say 2 pi is over here. And let's see, let's draw cosine in dark blue. It's going to start at 1 and end at 1. At the halfway mark, it's going to be at the -1. And actually, let me keep drawing lots of wiggly waves. This cosine goes for forever. Okay, that might not be the best graph, but you get the idea. Okay. Then why don't we draw maybe in red y equals to -1/2, which is going to be right here. Now, what's kind of weird is that the picture's kind of shifted a bit, right? We're looking for where the x values are the same. So notice that it's cosine of x now instead of cosine of theta. And this is now y equals to -1/2, which is different than how I set it up with the unit circle approach. I chose it to be x equals to -1/2. Okay, now let me explain the reasoning for that, because this is kind of tricky, right? I chose x because cosine is x in the unit circle perspective. So that's why I drew the red line x equals to -1/2, which is a vertical line passing through -1/2 on the x coordinate. But if I want to use it using the graphing approach, I have to switch my brain around. The x-axis is basically my angle, and then my y values is basically the output of the cosine function. So it's kind of a totally different perspective, even though it's representing the same information. It's like, remember when I did the wet noodle and I did the like kind of the real line twisted up as like the spring? So if you think of the real line as kind of like the straight noodle, and then the twisty noodle is the unit circle, it's like taking cosine function and straightening it out. That's how you get the blue line. All right, so from this perspective, you can see, well, there's going to be infinitely many intersections. Okay, it's just much harder to see what values they intersect at. So, of course, you know, if you draw a really nice picture, this is pi, you know, and that's supposed to be 2 pi over 3. And this is supposed to be 4 pi over 3, because we already know the answers from before. So I think what we could do is let's go to open up Desmos. If we want to graph, let's do y equals. And if we want to go to, actually, let me hide my bubble so that we can see. Okay, I'm going to click on functions, and then click on cosine, and then type x. Okay, there's our cosine, looks nice. And then let's also graph y equals -1 divided by 2. What's nice about Desmos is that it kind of automatically looks for intersections. So you can see that we can have a bunch of them here. And if you're lucky, it'll actually figure out the, actually let's not click on so many of them. Let's click on maybe those two and zoom in a bit. Let's say this and this. So notice that the first time we intersect, it's 2 pi over 3. And the second time, it's 4 pi over 3. So notice this is about 6-ish. So this is 2 pi. So within 0 to 2 pi, our kind of basic interval, we have 2 intersections where they meet. Everything else will just be built from this intersection. Okay, so the graphing point of view is good if you can use technology. So this is something that you want to use on homework. But it's much harder to do if you're doing it on a test, because you're not going to have Desmos to use on a test. So let me put hard to see unless using technology, which for us, I like using Desmos, but whatever graphing calculator that you use is what you can figure this out at. All right, really good and super important question. I'm not going to tag it as a GTQ because it's too easy, but it's very important that before you move on to anything else, you understand both of these approaches. Okay, time for some new examples. So the next problem we're going to think about, and let's zoom in a bit. Next problem here. Sine theta equals root 2 over 2. And actually, I'm going to bring my picture back. Hello. Okay. So as before, we already have the sine theta isolated. So this time I'm going to have sine theta equals root 2 over 2. Now sine I associate with the y coordinate, so I'm going to look for the graph of y equals root 2 over 2. Draw a unit circle. Okay, and I'm going to draw y equals a number is now a horizontal line. Okay, now you probably know, let's draw some whiskers here, that root 2 over 2 is a special number and it is associated with pi over 4. So actually what we found is one of our solutions is going to be pi over 4, this radian right here, and that's this intersection, and we're going to have one more over here, let's do it in purple, which is going to be 1 pi over 4, 2 pi over 4, 3 pi over 4. Okay, so those are the two solutions that we're going to have in the interval from 0 to 2 pi. So visually we're going to have theta is equal to pi over 4. Theta is equal to 3 pi over 4. Then we have to think, okay, how many solutions do we need? Do we need just one solution or infinitely many? Since it just says solve with no further instructions, we should interpret that as to find all solutions. So I purposely wrote this in as basically vague. So if it's not there, interpret it as all, which means I'm not done. I just found two solutions. To get all of the other ones, because sine is 2 pi periodic, we're going to add plus 2 pi k. Same thing to the next one. And instead of putting in a comma, sometimes I like to put the k right below both of these, since I'm going to use the k in both formulas, and then put a box around all of it. But pretty nice. There's not too much work to do. All of the work and all of the thinking is happening while we actually draw the unit circle. Now, I know if you have a test, you usually have your good cheat sheet, and then you're going to have your unit circle in front of you to stare at. So you might be tempted to be like, why do I even need to draw this unit circle? Why can't I just look at my unit circle that's filled out on your cheat sheet? And you certainly can. I mean, you know, this is the way I like to do it, because when I grew up, I didn't have cheat sheets. I had to, you know, my teachers made me memorize everything. So I kind of had to invent these kinds of tricks to help me visualize solutions when I wouldn't have a unit circle. So I think the more that you can memorize, the quicker you can solve problems in the future. So it's almost like you're doing it a little bit slower now so that you can do these kinds of problems faster once you get to calculus. And it helps the idea stick into your mind, is if every single problem you're drawing a fresh little unit circle, I promise you, it really pays off by the end of the term. Okay, I think we're ready for the next example. So for this section, I think it's so important. I'm going to do basically all of the problems. Okay, now we have a new problem here. Sine theta equals 1/5. So right by now, you know the drill. We're going to solve sine theta equals 1/5. Sine you associate with y, so we're going to look for y equals to 1/5 intersection. So as we draw our picture, x and y. Okay, y is 1/5. One way to think about that is, remember, this is unit circle, so that point above is 1. That means 1/5 is, if 1, 2, 3, okay, that's cutting up the circle into 5 equal pieces. 1/5 is right here. So just like in the last problem, you see that there are two solutions, one here and one here. But 1/5 is not a standard angle, right? So if you actually think about what the theta is, or the t, the wet noodle, there's one of them is right here. Okay, and then there's another one that's purple. Let's do it purple right here. going on the outside. Let's make sure we can see both purple and, okay, and then let's call this, actually let's label them like this, theta 1 and theta 2. Okay, clearly I hope you can see visually they're two different angles. So this is what I think the power of drawing this picture is here for, because if you actually try to solve for theta, you might be thinking, hey, wait a minute, why don't I just do this? You know, we learned inverse trig functions, so why don't I just do sine inverse on both sides of the equation? Sine inverse and then sine will cancel out, giving me theta. So I can basically just do sine inverse of 1/5. Sine inverse of 1/5. Okay. You know, I should have, let me actually pause the video for a second. Okay, I hope we are rolling again. All right, so I've got our calculator pulled up here. So sine inverse of 1/5. We can go to the calculator. Give me a second. Go. So we have to hit on this one, second sine inverse, and then do 1 divided by 5. Hit enter. Okay, and it gives us a number. So I'm going to write that number down. 0.201, and I'll write it to, let's see, the instructions actually tell us round to the nearest thousandth, which is 3 decimal places. So looking at the calculator, I'm going to go 1 decimal place is the 10th, 2 decimal places is the 100th, 3 decimal places is the nearest thousandths with the th. So 201 is my number rounded correctly. So, okay, here's where, by thinking of everything as a wet noodle, you're at an advantage, because now you know, okay, the calculator is only giving me one answer, but I know from the geometry of this problem, by drawing this horizontal red line, drawing a unit circle, I know I actually have 2 solutions. Which one is which? This 0.201, we have to think, remember, why are we using radians? We are using radians because remember, 2 pi is about, you know, if you type that into the calculator, is a little bit more than 6. It's like 6.2. That's 1 full turn, the length of the circle. Pi is the length of half of the circle, which is about 3.14. Divide that in half, you get 1.57. That's a quarter circle. And then shrinking it, right? 1.57 is a quarter of a circle. 0.2 is going to be much, much smaller than that. And in fact, we visually know that what this number is the theta 1. So, how do you get theta 2 without, the calculator is not going to give it to you. You have to think. You have to use reasoning to get to it. So pause the video and see if you can come up with this on your own. All right, welcome back. How do you get theta 2? This is the magic. Pi, if I do it in blue, right, that's pi. That's the full semicircle. That's not what we want, right? We want theta, which is the purple piece. But notice that this part here is going to be exactly the same as the part on the other side. So basically, if I subtract theta 1 from pi, that's going to give me theta 2. So if I do this on my calculator, you know, pi is about, I'm just going to write it as pi. We're using theta 1 is about 0.201. Okay, let's figure out what that is on the calculator. So let's do pi minus 0.201. Okay, this is our 2.94, and I want to round to 3 decimal places, so I see that the next digit is 0, but the next digit after that is a 5, so I'm going to bump it up to a 1. Okay, so now I have theta 1, and now I have theta 2. What we're going to do is we're ready for our final answer. So theta, our solutions are 0.201 plus 2 pi k. Theta is going to be 2.941 plus 2 pi k. K belongs to an integer. Those are our solutions. Now that we've finished that, tack GTQ, because I always ask a question where you have to solve and think about it and know how to use your calculator responsibly. So I always talk about, like, using your calculator ethically and responsibly. This is what I'm talking about. Like, the calculator is the right tool to solve this problem because sine of theta equals to 1/5. The radian measure for that is not a nice number. The radian measure is, 0.201 or 2.941. You can't do that without the calculator. But without drawing the picture, you're not going to see the beauty of the geometry, and you're not going to know how to interpret the number, right? You now know that 0.201, you know what it means. You have this very visual graph of the little tiny arc of the circle, and the terminal point for that is exactly where the y-coordinate is 1/5. If you measure the arc in purple and you stop here, that arc length is 2.941 radians, and the terminal point also has y-coordinate 1/5. Beautiful, beautiful problem. So just wanted to do that. All right, let's get rid of the calculator and let's solve the next problem. Okay. Tangent x equals 5. Let's tag this one as a GTQ as well. All right. So for this problem, I'm going to actually not use the unit circle because we're using tangent. I'm going to use the graphing approach, where I'm going to set it up as y equals tangent of x and y equals 5. Now, since I'm using the graphing approach, we should know what tangent looks like by just doing a quick sketch. Now, of course, if you make a good cheat sheet, you would be able to look at your cheat sheet so that you can copy and make a quick sketch in your problem space where you're going to solve it. So I already have these memorized, so I don't need to look at anything. I can just know that I'm going to have an asymptote at minus pi over 2, positive pi over 2, and my tangent looks something like that. Tangent of x. You know what? It always bugs me if it doesn't have the arrows, so I'm going to put them there. Even my asymptotes should have arrows, but I'm not going to be too much of a stickler. Okay, now let's think about this problem, because this was another problem that we actually need technology. So clearly, if I draw y equals 5, I can do that. And let's pretend that's 5. So y equals 5, and we've drawn in blue y equals tangent of x. So what we're looking for is we are looking for where these intersect. And I hope you can see that visually we have a solution over here. Now, are there going to be more solutions to this? Yes, but it's not going to be on this blue picture, right? It's going to be on all the other copies of tangent as we keep repeating it by the period. So as we think about the solution, we're going to say, okay, tangent of x equals 5. I'm going to do tangent inverse of x. Oops, tangent inverse on both sides. So we're going to get x equals tangent inverse of 5. And now we need the calculator, because that is not a nice number that we can do using the unit circle. So we're going to go to, let's just clear that, second tangent, 5. There we have it. So it tells us it's, so again, rounding to the nearest thousandths is 3 decimal places, so 1.373. Okay, so that's going to be the only solution on our principal branch. But remember, it doesn't give us any indication of restrictions. It just says solve this. So there's more solutions. All the other solutions are going to be plus the period. Now the period for tangent, remember, is pi. So when I write my solutions, instead of writing plus 2 pi k, now I do plus pi k, where k belongs to z. Okay, so let's do this on Desmos just so that we make sure we understand the concepts. So let's delete these and let's draw, let me hide my face. Hide the calculator. Y equals tangent. Let's draw that first. Okay, and then y equals 5. Okay, and let's zoom out a little bit. You can see there's infinitely many intersections. The one that we found was this one. And lo and behold, we get the same decimal, 1.373 rounded to the right decimal. And then if you add pi, you're going to get all of the other ones right here along these intersections. Cool. All right. Let's bring back all the good stuff. All right. So those are all the equations where basically they're all with tangent or with one of the trig functions on one side of the equation. All right, what's next? Let's look at some new examples. So let's get rid of the calculator. Okay, so new examples where we have to do a little bit of algebra to get us to the ideas that we did previously. Again, it just says solve the following, give the exact answers if possible, round to the nearest thousand when necessary. So on the test, I'm always going to give 0 points if you solve it with the calculator when the calculator wasn't needed. So you have to know how to do this stuff without the calculator and only use the calculator when the problem demands it, like we saw earlier. All right, but let's jump into the solutions here. So let's look at part A. What's our first equation here? First equation is 1 plus 2 cosine theta equals 0. So, what we're going to do is we're just going to isolate the cosine and then see what we get and see if we can solve the problem using the methods of before. So isolating the cosine, let's start by subtracting 1 from both sides. 2 cosine theta equals negative 1. Then let's divide both sides by 2. And we reduce to cosine theta equals to negative 1/2. All right, so negative 1/2 is a special value. So we should be able to use the unit circle method to help us solve this. Now remember, cosine is the x value. X value is negative 1/2, gives us this vertical line. We see that there's 2 intersections. And then we have to think, okay, what are the 2 solutions? Here, this is going to be 2 pi over 3. And again, use your full filled out unit circle to help you. Just to confirm that if you look at the x coordinate for 2 pi over 3, that it really is negative 1/2. That's another way to confirm that you're doing this correctly. And just for this problem, I'll just write it, the solution in using negative 2 pi over 3 because it looks nicely symmetric. And check this out. So what are all of my solutions? They're going to be plus or minus 2 pi over 3 plus 2 pi k. K is an integer. So as you can see, I'm showing you some new tricks each time we do it because we actually already solved this problem. This time I'm going to write it in an even more compact form where I'm not even going to write it as 2 separate solutions. I'm going to write plus or minus 2 pi k. Sorry, 2 pi over 3. You can write it as two separate lines like we did in, I think that was the very first example. So let me actually just show you. This is the same equation that we solved as our first example, which is up here. So two different ways to do it, but they really mean the same thing. Great. So before we start part B, I want to give you the opportunity to pause the video, see if you can do this equation on your own, and when you're ready, hit play. Okay, welcome back. So here's our next equation. Our first step is to isolate the trig function. Okay, so first let's write this as 3 tangent squared theta. And I'm going to go ahead and do one algebraic step. I'm going to add 1 to both sides so I can write equals 1. Then let's go ahead and divide by 3. We have tangent squared theta equals 1/3. And now let's go ahead and take a square root. Don't forget, when you take a square root, you're going to do plus or minus. So we've isolated tangent theta as tangent theta plus or minus square root 1 over square root of 3. So tangent theta is root 3 over 3, or plus or minus. So for this one, we've solved it using the graphing approach, so I'm going to do the same thing here. Let's draw it right here. We have plenty of space. Let me check my algebra. Okay, so this one's really tempting to think that we have a clean answer for this, but there isn't. I'm pretty sure that this one doesn't have a nice clean solution. Okay, so here's our tangent. So y equals tangent x in dark blue. Let's do purple. So here we actually, because we actually do want both plus or minus, we're actually going to have two lines. So one of them, I don't know what root 3 over 3 is. Let's check real quick. All right, so if you ever get this where it just gives you the exact answer, that's what this double arrow is for. If you click on that, it gives you the decimal approximation. And if you're lucky, sometimes it can go backwards. So, oh, we are lucky. All right, so about 0.577. I'm not going to try to draw this too accurately. So we got two of them, though. Okay, so from here you can see that we've got two solutions that we need to solve for. So for this one, we're going to write it as tangent, it's going to be tangent inverse of root 3 over 3 is going to be one of them. And then theta is equal to be tangent inverse of negative root 3 over 3. Okay? So we should be able to get two different values on our calculator for this, and those are going to be the solutions that we seek. So let's do second tangent inverse. So it's square root 3 divided by 3. So don't forget to use the little arrows to move outside of the square root so that you're calculating things correctly. All right. So we're going to get 0.524, rounding to 3 decimal places, 524. Okay, now let's evaluate the second one. tangent inverse minus, so remember minus is down here, and now we do square root 3, right arrow to get out of the square root, divided by 3, close parentheses. All right, and then we get negative 0.524. Which, if you look at our graph, we could have probably anticipated that. Notice that, remember, tangent is an odd function. So if you remember your identities, your even odd identities, tangent's odd, you're like, oh, I could have saved myself a step of typing in the calculator, but I didn't think of it in time, so I did it the slow way. But hey, you know, be better than me. Try to do it even better on the test. All right, so the key here, though, is that these are two different solutions. They're not the same. So when I do my pi periodicity, I'm going to add plus pi k, k belongs to z, and then these are my solutions. Okay, sweet. So we've pretty much done the lesson, so let's just summarize. The first couple examples were all where we had one trig function by itself. Showed you two methods using the unit circle and the graphing method, and we talked about what to do when we have to use the inverse trig functions to get the exact value, approximate values. So what's next? Next, we're going to do just yeah, there's two more examples, and I might as well just do them all. I already did this video, 40 minutes, let's keep going. Okay, next, let's think about what I like to call the zero factors property. It's something that you probably learned in algebra, maybe didn't call it this, but let's just review it. Here's what it tells us. It says, okay, assume that we have, if we have a times b equals 0, we already know that, if a times b equals 0, well then it has to be true that either a is 0 or b is 0. Okay, and that makes sense, right? So if we do this logically the other way, right, if I know a is 0, then a times b clearly will be 0, right? If b is 0 and I plug in b into the equation, then a times b will also be 0. But what's interesting about the zero factors property is it's going in the reverse direction. If I know that two numbers multiply to be 0, well then what we can do is we can conclude that one of them had to be 0. That's what this says. So it's really, really helpful, especially for solving equations. All right, so let's solve this next problem here. So we've got 3 sine theta tangent theta plus 2 sine theta. Okay, looks pretty complicated compared to the previous problems. But let's just keep our cool. As always, if you don't know what to do, I usually start writing the problem and my brain starts thinking as I write. So, okay, here's the problem. I don't recognize any obvious trig identity, so there must be something else we can do, and maybe a simple algebra trick can help us. Do you see it? Do you see how we have sine theta in both terms here? So why don't we factor it out? So let's just pull it out front. If I pull the sine theta out, what will I have? Well, this no longer has the sine theta, so we're going to have a 3 tangent theta left over. And then this sine theta is no longer there, so we're just going to have a 2. Okay, so what we've got now is we've got sine theta times this other piece. What we're going to do is let's use the zero factors property to basically split this into 2 separate equations. What we can say is, okay, sine theta is going to be equal to 0, or we're going to have that 3 tangent theta plus 2 is equal to 0. So instead of solving one hard equation, we split it up into 2 simpler equations. All right, pause the video, See if you can get the solutions to these on your own. But let's keep going. So let's solve sine theta equals 0 using the unit circle method first. Here's our circle. Sine theta, we know we're looking for when the y values equals 0. So basically, there's our y equals 0. These are our two solutions. So we can immediately basically write down the solutions are 0 and pi. Okay, 0 and pi. So if I want to write down all of the solutions, I'll just write, actually let's write it slightly differently. Let's write it as 0 plus 2 pi k. Theta is pi plus 2 pi k. Okay. All of these will solve the original equation because sine will be 0 at these values, and it basically will make the equation true. Sweet. Now, as we look at the second equation, it's too difficult to solve in that form, but we can just do a little bit of algebra. Move the 2 to the other side, divide both sides by 3. Not one of the nice clean values of tangent theta, but we know what to do here. Tangent inverse of negative 2/3. Also, even though you just probably were dying to do this on the calculator, draw a quick picture. Really, I will hope to instill that if you draw pictures, it helps you not make mistakes. There's value to these because it really is conveying a lot of information at once. Okay, tangent, we're saying, okay, what y value is like negative 2/3? So basically, y equals negative 2/3. Where do they intersect? You can see that we should get a negative number for our angle. And let's pull up the calculator. Let's clear it. Second tangent, and we want to do negative 2/3. So just to explain real quick, why did I immediately know to jump to the calculator? Well, because I pretty much have my unit circle memorized, and I know that the only values for tangent that have values on the unit circle are √3 and 1 and -1. So either positive or negative √3 or positive and negative 1. Those are the clean values. I think there's one more. What's the other one? 1 over √3 if you do, yeah. Okay, so anyways, negative 2/3 isn't one of those. So we do need to round and to the nearest thousands. So negative 0.588. Notice that the negative sign of the calculator agrees with our picture. It's saying that, okay, great. I was expecting a negative number because of the picture. I get a negative number, so I'm super happy. Now, tangent has period pi, so we're going to do plus pi k. So the other solutions, let's just write it like this. Great. Actually, there we go. I'll just, since I wrote it in the line below. Okay, great. One more problem. So if you need a break, feel free to pause the video and you can always come back. But we have one more to go, so let's just power through because we're so great. We love math. It's super fun. Pro tip. Last example ends with a cool pro tip. So I'm going to call this U substitution. So what is it? I recommend you use U substitution where we're going to rewrite the equation in U. So if you've never learned this technique, you're going to use this technique a lot in calculus, but it's a technique pretty much from algebra. So here's what we're going to do. Let's look at the problem we're going to try to solve, and I'll explain the technique of U substitution as we solve this problem. So first, let's just write the problem. 2 sine squared theta minus 15 sine theta plus 7 equals 0. Really complicated. Way more complicated than what we've been doing. So here's the big idea. Little light bulb. So what's u sub? U sub is my shorthand for u substitution. What we're going to say is like, wait a minute. So I see that basically I have 2 times sine theta squared minus 15 sine theta. Why don't I actually introduce the new variable u, where I'm going to write u is equal to sine theta. So this is kind of the big key idea here. And you're thinking, okay, why? Well, let me just show you what happens if we do this. So just suspend your belief for a minute and just follow along, okay? And I'll answer why in a bit. If I say u is sine theta, then I can rewrite our equation as 2u squared minus 15u plus 7 equals 0. All of a sudden, this equation is much easier to look at. And it's just a quadratic equation. Just by switching it to a new variable, it makes it clearer and easier to recognize the pattern. Now, with a quadratic equation, you have a bunch of methods for solving this. Number one is you should start by seeing if it factors, and if it doesn't factor, see if you just jump straight into the quadratic formula, unless you see some clever observations. But those are the two main techniques. So let's see if it's going to factor. To do that, we're going to need to come up with some brackets. Now, because 2 is prime, we'll have 2u and u. That'll give us our 2u squared. And 7 is also prime, which means either I'm going to put the 1 and the 7 here, or I'm going to put the 1 and the 7 in the reverse spot. So let's pretend we put them in this spot first. Would I get minus 15u? So this would give us 2u, and then this would give us 7u. So I could either get 2 plus 7 or 2 minus 7, things like that. That's not going to get me to 15. So putting them in this spot is not going to work. So maybe you see what to do. You're like, oh, wait a minute. But if I put the 7 over here and the 1 over here, then I can do 2 times 7 is 14. And then this will give me u. 14 and 1 gives me 15. So then I'm like, oh, okay. Well, why don't I actually pick minus minus, which I'm allowed to do, because if I do minus minus, I get negative 1 times negative 7 is positive 7, which is what we need out of this equation. We need this to be positive, and we need this one to be negative. So, huzzah, we factored it. Pretty special. And then we have, okay, we have factored equals 0, time for the 0 factors property. So, this allows me to simplify it to two new equations. 2u minus 1 is equal to 0, or the other equation is u minus 7 is equal to 0. So let's solve these equations. 2u is equal to 1, u is equal to 1/2, and this one's even easier, u equals 7. Okay, great. We were able to solve the equation in terms of u. We now have two possibilities, but we got to go back to the original variable. Okay, that's what I put in this really big font, old person bold. Put the little dangerous curve. Make sure that when you take notes, you can actually remind yourself, and I did a gigantic squiggle here to remind you. We're not done. The original problem wasn't to find the variable u. We added that to kind of help us. But we actually are not done. What we actually go to next is we go, okay, if u is sine theta, replace the u. I actually have to solve these two new equations here. Sine theta is 1/2, sine theta is equal to 7. Okay. Sine theta is 1/2. I can draw a quick unit circle. Okay. Sine is the y value, so when is the y value 1/2? See, there's two solutions here and here. This is going to be, for angle theta, is going to be pi over 6 plus 2 pi k. And the other angle is going to be, gosh, what is that? 1, 2, 3, 4, 5 pi over 6. So I usually just do it with my whisker method, because you think I'd have the unit circle memorized by now. I don't. I did when I was a student, but now I can only keep so much info in my brain as I get older. So I just, I know how to get the right values. Let me add my z. Okay, what about the next picture? Sine theta equals 7. Okay, so here's my unit circle. I can't even draw y equals 7 accurately. It's way up here. Is that red line going to intersect our circle? So this has no solutions. Okay, so it's kind of obvious, right? The sine is the y value on the unit circle, and 7 is just way too big. It's way too high, so I'm never going to intersect it. If you look at the other approach as well, if I draw a quick little sign, these are always going between 1 and -1. 7 is way up here, also never going to intersect. Third way to convince you. See if the calculator can do it. Let's try second sine inverse of 7. Error, domain. There is no value for that. You can't put in 7 into the inverse trig. Remember, the inverse trig functions only can eat in the domain -1 to 1. All right, there you have it. A full lesson. I did everything for this section. It's one of those important sections. So I hope you enjoyed this video. Take your time as you work through all the examples. Make sure you master every example here, every ICA, every homework from 7.4. It's one of the really key building block sections for not only our class, but any other class that you're going to study in the future. All right, thanks so much for watching, and I hope you have a great day. See you next time.